Hello students, welcome back to MAGESH classes. This is the third part of the electrochemistry. In this presentation, we are going to discuss about variation of molar conductivity with the concentration. Before entering into the topic, if you are the new to this channel, don't forget to subscribe for more videos. Let us enter into the topic. Variation of molar conductivity with the concentration. The scientist Friedrich Kohlrausch studied the molar conductance of different electrolytes at a different concentration. So we have studied that the molar conductivity is the conductance of the electrolytic solution which contain 1 mole of the electrolyte. So at the end of the study, the molar conductance is directly proportional to dilution or inversely proportional to the concentration. More is the concentration, the molar conductivity is less. Molar conductance of an electrolytic solution increases with the increase of dilution. When the dilution increases, that means the concentration decreases and then the molar conductance increases. Kohlrausch deduced the empirical relation. He derived the particular relationship between the concentration and molar conductivity. Molar conductivity is given as the term lambda m and concentration is C in molarity. What is this equation? That is lambda m is equal to lambda m naught minus k into root C. Here the lambda m is the molar conductivity of the particular electrolytic solution and the lambda m naught is the limiting molar conductivity. So it is the conductivity at infinite dilution, that is completely concentration reaches zero. The conductivity is the limiting molar conductivity and k is the constant and C is the concentration. Kohlrausch reduced the empirical relationship between molar conductivity and the concentration. Concentration is C and molar conductivity is lambda m, and lambda m is m naught is the limiting molar conductivity. So lambda m is equal to lambda m naught minus k into root C. This equation is in the form of y is equal to mx plus c. That is in the form of linear equation. The plot of lambda m versus root c gives a straight line with a negative slope, and the slope is equal to minus k, and y is the intercept. So what is y? Here we take x-axis the root c and y-axis lambda m, and you get the slope minus k, and intercept is equal to limiting molar conductivity, that is the conductivity at infinite dilution. Let us discuss about the molar conductivity of the strong electrolytic solution versus concentration. So Kohlrausch equation is in the form of y is equal to mx plus c, and the plot of lambda m versus root c gives a straight line with the negative slopes. Here the strong electrolytes give examples KCl and NaCl. It is completely dissociated, and the Kohlrausch equation is lambda m is equal to lambda m naught minus k into root c. The plot of lambda m versus root c gives a straight line. In the x-axis, concentration term is taken, and in the y-axis, lambda m is taken. So in the x-axis, root c mole inverse 1, and in the y-axis, lambda m, the unit of lambda is Siemens meters square mole inverse. For strong electrolyte, the graph is in the form of straight line, and for the weak electrolyte, it is in the form of parabola. That is, the curved line is obtained. So this is the graphical representation of the Kohlrausch law. At high concentration, the lower molar conductivity is observed. What is the reason? At high concentration, low molar conductivity is observed. What is the reason? So in the graphical representation, we have seen that for weak electrolyte, it is a parabola, and for strong electrolyte, it is in the straight line. So the molar conductivity, when the dilution increases, molar conductivity slowly increases. At higher concentration, the molar conductivity is very, very low. The reason for is, at higher concentration, the number of constituent ions, for example, sodium chloride, it contains Na plus and Cl minus ion. The number of constituent ions of the electrolyte in the given volume, for example, 1 liter, is high because it is in the higher concentration, and hence they are very close to each other. As a result, the attractive force between the oppositively charged ion is high. As a result, what happens? The movement of the carrying the current by the respective cations or anions towards a particular electrode is decreases. And so in that higher concentration, we observed low molar conductivity. One more reason, the ions experience a viscous drag due to the solvation. So it is in the water or in any solvent. The movement of the ions is dragged by the solvation of the solvent. So the ions experience a viscous drag due to the rate of solvation. At higher concentration, the molar conductivity is low. As dilution increases, the ions are far apart and the attractive forces decreases. The distance between the ions increases when the dilution increases. When the dilution increases, the conductivity slowly increases. At infinite dilution, the ions are so far apart and the attractive force, that is the interaction between the ions, is negligible, insignificant, and it reaches a maximum value at infinite dilution. The lambda m is the limiting molar conductivity. What is that molar conductivity at the limiting condition? The limiting value of molar conductivity when the concentration of the electrolyte approaches 0. At infinite dilution, when the dilution is completely obtained, the ions are so far apart and the attractive force is insignificant and reaches a maximum value at infinite dilution. So it is completely, the attractive force is neglected. So it has a maximum value of molar conductivity at infinite dilution. The lambda m naught values for the strong electrolytes can be obtained by extrapolating this straight line. By extrapolating, and it reaches at y. It is the intercept area. This intercept area corresponds to the lambda m0 value in the graph. For weak electrolytes, acetic acid, it is partially dissociated. The plot of lambda m versus root c gives a curved line. It is at a parabola. At higher concentration, the plot is almost lie on the x-axis. It is almost parallel to the concentration axis. As dilution increases, the conductivity also increases. At a particular concentration, that is the concentration closely approaches 0, there is a sudden increase in the molar conductance. This is because the dissociation of weak electrolyte increases with the increase of dilution based on Ostwald dilution law. And the curve is almost parallel to the lambda into the y-axis. We have seen that the lambda m naught, that is limiting molar conductivity at 0 concentration, is obtained for strong electrolyte by extrapolating the straight line, and it cuts at the y-axis. But for weak electrolytes, we cannot be obtained by extrapolating the plot because the plot is a non-linear, so it is a parabola. How the lambda m naught values of weak electrolyte is calculated? For strong electrolyte, by extrapolating the straight line, and it cuts at the y-axis, the lambda value correspond to is lambda 0 m, that is limiting molar conductivity. How these lambda m naught values for the weak electrolytes is obtained? It is calculated by Kohlrausch law. So we will see it in the next session. Okay, students. After this, we have stopped this presentation. Thank you for watching.